this address, but just hard code values to make sure you cover all the operations. Don't hard code all these values. Just hard code, write the hard coded values inside your instruction memory, only to cover the do all the functional coverage. Like you have so many operations, you'll be covering until this point. So make sure you write the instructions such a way that you cover all the instructions. Okay. And register file. Register file has a clock. It has clock, reset, which is reset is synchronous reset. So it will work with respect to clock edge. And you have write enable, read address, two read address, two read data, one write address and one write data. So you will be reading and writing at the same time. You'll do the writing at the positive clock edge of clock. So that is why you have clock inside the register file. You will write at the positive clock edge of positive clock edge, but reading is asynchronous. Okay. And here nselect is 3. Make it 5, because you have RS, RT and RD, which are of 5-bit length, so it should be 4 down to 0. So nselect should be 5. Okay. And you have data memory, which is of 512 word cross 32 bit. So it is of memory. Like this is of 32 bits. And like this, you will be having 512. Okay. So this is your data memory. For that you have clock, write enable, address which is of 32-bit length, and you have data in, because when you do store word, so you'll be writing some data inside the data memory. That's why you have data input, and you have data output, because when you run the load word, you'll be accessing the data. That is why you have data out as the output. So these are the instructions. Add the one the function 6 bits that is ending with 1 are the immediate instructions. So you have 2 add instructions, 2 subtract instructions, you have 2 jump instructions. So the LSB ending with 1 is the immediate instruction. So LSB ending with 1 is the add immediate. LSB ending with 1 here is the subtract immediate. So LSB ending with 1 is the jump immediate. Okay. Assignment deliverables. Your submission should include the following: block designs in VHDL and your test bench in System Verilog. System Verilog test bench capable of preloading memories and verifying the correct functionality of the processor using a simple test MIPS program. A comprehensive report of the design and test bench architecture. In the report, include the information on how you have to make sure the processor works fine. And if you have found any bugs in your design, mention that in your report as well. Okay. So this is a brief overview of your assignment. Now I'll go through each and every blocks in your design. Okay. Any questions?
Question.
Yes.
How tall should the memory area for the ROM be? Because we're just putting in the 31 bit for the bit for the address, it complains that the number overflow because 232 is a little bit too large.
One more time, sorry.
Sorry. So the memory width, so in the instruction gauge, the width is 32 bits, right?
Yes.
But how many of them?
Instruction memory?
Yes.
Okay. Maybe 10 or 12.
Okay.
Because as I told you before, you have to just make sure you cover all these instructions. Like you have to do functional coverage for these instructions. So there are like 3, 10.
Okay.
Max, it might be 15 max. You might make it 15 address.
Okay.
Okay.
Thanks.
First, we'll go through the data part. So your program counter has three inputs and one output. Okay, it has reset as input, reset clock, and this data. Okay, and it has one output, and you have program counter, clock, and it has input which is reset of 1 bit length, clock of 1 bit, then you have input of 32 bit length and output of 32 bit length. So this will go inside into the adder. And the output of adder will be 32 bit. And you will be adding 1 every time. Okay, so program counter is used to because in your instruction memory, this is your instruction memory. You'll be having 32 bit values, right? Are you aware of the instruction format? Okay, let me go through that first. So this is your instruction format for MIPS. Okay, you have function which is of 5 bits.
6 bits?
Yeah,
6 bits.
yeah, 6 bit. You have opcode of 6 bits, then RS, five bits, RT, 5 bits, RD, 5 bits. So this is function is of 6 bits, and this is of 5 bits. So if you sum up, you'll get the 32-bit. Yes.
Just real quick, could you just say what RS, RD, and RT were? What the variables stand for?
Yeah, I'll explain that when I explain your register file. I'll explain you what are those.
Okay.
Okay. So this is your instruction format. Okay. Like RS is the input address for operand A, because for operand A you have to access some 32-bit data, right? That will be addressed. That you can fetch that data only if you have RS value as an address. So RS is the address. So that address value will be encoded inside your 32-bit address. Okay. So this corresponds to operand A data, RS. RT corresponds to operand B. Okay. And RT is the destination. So it is write address. Okay. Based on what operation you have to do, like say if you want to do this and say add operation, then your function value will be 1 followed by 5 zeros. Okay. And this is R type of instruction, so your opcode has to be 6 zeros. Then say you are fetching the input data from the first location, then it should be all 5 zeros. Okay. And say you are fetching the second operand B from the second location, then it will be 4 zeros and a 1. And say you are writing the third location, then it will be 3 zeros followed by 1 0. Okay. And just ignore this as of now. So let's make it all zeros. So if you consider all these 32 bits, you have to give this 32 bits as address to your controller, so that it can decode this, and then you will be able to do add operation. Okay. So this is how you come up with the address. Any questions? Yes.
You're gonna go over the difference between the I type and the R type later, right?
Yes.
Okay.
Any questions? Is it clear? Okay, so this is a program counter. So to fetch that, so this 32-bit address will be stored inside instruction memory. Okay, if you want to fetch that instruction, then you have to increment your program counters. So you will fetch the instruction one by one. So it is something like this. So that 32-bit value will be stored inside instruction memory. Instruction memory is of, as I told you before, 2 power 32 minus 1. So it starts from 0 and it goes up to 2 power 32 minus 1. Okay, but you won't be hard coding all these till up to this value. You'll be just hard coding up to say 15 values. Okay, so program counter is here. So if first your program counter, you have to make reset high so that your program counter will be 0, all zeros. So first you'll be fetching this instructions. Okay, and that 0 goes into the adder and it gets added, that increments to 1. So next you will fetch this data. So it keeps on incrementing and you have to fetch until this data. Okay, so initially it will be all zeros, all zeros, then it will increment to 1, then 1 0, 1 1, 1 0 0, okay, and goes on. So say that we have fetched this instruction now, okay, so that address, so the output of this PC is all zeros. This is of 32-bit, right? You will be having all zeros. So that address will be given to the instruction memory. So this is the operation of program counter. It's basically like a counter. It increments from 0 to, it can increment from 0 to this value, but if you are able to fetch until this point, it's fine, okay? So now you have the, let me get the timing diagram for that. Clock, reset, and okay, so, and say you have reset as high initially and it goes to low, and you have the clock. So let's consider the positive clock edge. Okay. So initially, as reset is high, you'll get PC out as 0, 0. So until this point, I'll be having all zeros. Okay. At this positive clock edge, reset goes low. So your PC, your program counter starts incrementing, right? So it's 1, 2, 3, and it keeps on incrementing. So this is how your program counter works. Any questions? Is it clear? Okay. So next block is instruction memory. As I told before, your instruction memory will be having hard-coded values, 32-bit length. Say it might have initially, okay. So this program counter will initially point to this location. So we'll be fetching this data. So that is the operation of instruction memory. Okay. Based on the program counter address, you have to fetch the corresponding data. Okay. That will be the output of instruction memory. Okay. Any questions? So the instruction that comes out of this instruction memory will go inside the controller. Okay, controller does both the controlling and decoding operation. So I'll explain the controller later, but it will be something like this. As I told before, this is your 32-bit address coming out of instruction memory. 6-bit, 5. So this is function. RD, RT, RS, and upcode. Okay, so this is a 32-bit address which will be stored inside instruction memory. Now that has to be decoded, right? So wherein RS is of 5-bit. So once this 32-bit address goes inside your controller, you will decode it and you will do bit slicing, and you'll get RS, RT, RD, function, upcode. Along with that, you'll get the immediate value as well. Immediate value is nothing but if you bit slice this part, you'll get the immediate value. Okay. So RS will help you to get the operand A. RS corresponds to the operand B address, and RD corresponds to the write address, because once you do the computation, you have to store that inside register file. So that address will be given by the RD, destination address. And you have the function which is of 6-bit to select the corresponding operation in the ALU. And you have the upcode. I'll go through this function upcode later. And you have the immediate, because you have R type and I type of instruction. Okay, are you familiar with this? R type and I type. Do you want me to explain?
Yes.
Okay. So the difference between this is R type. Okay. For R type, this you're registered, right? So you have RS. I'll explain your register first, then you will be able to understand that. Okay. Okay, so this is your register file. So once you decode this address, you will get RS, RT, RD, these values. Okay, so that RS and RT are fed to the register file. You know that you have register file wherein you will be reading some data from register file and you will be writing some data to the register file, right? So you have RS and RT which corresponds to some which is the address wherein you will be able to fetch the corresponding data outside of your register file. Okay, registered you have read data 1 and read data 2 which are of 32-bit length, right? So you'll be writing and reading at the same time. Writing operation is done only at the positive clock edge and write enable has to be high. Okay, that write enable control signal is controlled using controller. I'll explain that later. Okay, and you have the write address, that is nothing but RD, because RD specifies where exactly the data should be written. So RD specifies the address, and to that location this write data will be written. Okay, write data will come. You'll get the write data from the mux. Okay, whatever the computation that has been done will be stored inside register file. Okay, and you have, so this is the operation of register file. Now we have I type and R type of instruction, right? So for R type, as I explained before, there is a straightforward method. Okay, you won't be considering this immediate. So you have the mux here. Mux is used to select between the mux. You have to select the operand B. So operand B, either it can be the output of the register file, or it can be the sign extended output. That will be selected using this mux. Okay. If you have an immediate instruction, then you have the first operand. If you have the I type of instruction, then the first operand will be coming from the register file. But operand you will get the operand 2 if you do the sign extension, because this 15 bits of immediate values will be fed to the sign extender. Do you know the operation of sign extender? Okay, so say you have 16 bits of values, right? 1 to 16. You have to consider the MSB here. Irrespective of these 15 bits, if your MSB is high, then you have to make your rest of the values. You have to extend the rest of the values till 32-bit with ones. Okay. If you have your MSB as 0, then irrespective of these 15 bits, you have to extend all the values with zeros. This is called sign extension. Okay, this will be done using this sign extender block. Okay, in this immediate instruction, operand 1, operand A, first operand will be coming from your register file, but the second operand will be the sign extent of this immediate value, because that immediate value, which is of 16-bit length, will be fed to the sign extender. That will be sign extended, and that will be fed to your mux. So when you have I type of instruction, then you have to select this value as operand B. So that selection between this and this is done using this select line. So that select line will be given by the controller. So I'll explain the controller later. So this is the operation of register file, and that is the main difference between I type and R type of instruction. Is it clear? No? Okay. Okay, now I will write the operation of both R type and I type. I'll compare both of them. I think it'll be easier for you to understand. I'll only write the active signals, okay? RS, RD, and here immediate will not be active. So if it is I type of instruction, it will be in this format. You will be having opcode of 6-bit, RS input address of 5-bit, RT of 5-bit, and the rest all you will be considering as immediate value, which is of 16-bit. Okay, but if you have register R type of instructions, then you will consider operand of 6-bit, RS of 5-bit, RT of 5-bit, RD of 5-bit, and function of 6 bits. Okay, this is R type of instructions. Whatever are written in red color will not be considered using by the mux, because it is R type of instruction. Okay, in I type of instruction, whatever are written in red color will not be considered, because I means immediate, so you'll be considering the immediate which are of 16 bits, and that you will do sign extension, and this value 32-bit value will consider that as the operand B. Okay, this is the main difference between R type and I type of instruction. Is it clear now? Any questions? Because this is very important. Can I proceed with the other blocks? Okay. And I would like to write the timing diagram for register file. This is the clock, reset synchronous, and we have write enable, read address 1, read address 2, read data 1, read data 2, write address, and write data. Okay, these are the signals. The clock. You have the reset. I will not consider the reset because it's easier for you to explain, because we'll be fetching the values from register file and we'll be writing the values, right? So I do not want to make it reset high, because if I make it reset high, then all the values will be 0, so there is no meaning in accessing the values. Everything will be 0. So I want to make reset as high. I want to consider reset as low here in this case. So let's keep it low. Let's say that we have the register file here, all zeros, one zero, and it goes on until 1111. But for my convenience, I'll just consider these 5 values. So say that we have stored value like 2, 5, 6, 8, 1. Okay. So say reset, the write enable will be initially low, then it goes high, then it stays low. Then we have read address. Let's make it okay. 5, 4, 2, 0, then 1, 3, 1. Okay, and write address as 2, 1, 3. Okay. Let's consider the positive clock edge, because for write operation we have to consider the positive clock edge. For reading, it is asynchronous. Okay, so reset is low, and read data corresponds to the read address, which is nothing but RS. Okay, I think now it makes more sense. Read address 1 is RS, this is RT. Okay, One second, write it here. RS, RT, and write address is RD. Okay. So initial value is at positive. Read is asynchronous. So 0 corresponds to 2 value, right? So it will be 2 here until this point, and then it's trying to read second 2, which is 6. Okay, and again it's reading 4. It means 1. Data is 1, and it goes on. And for RD2 corresponds to RA2, which is 1. 1 means we are reading 5 here, and it changes to 3, which is 8. Okay, and we are trying to read 1, which is corresponds to value data 5. Okay, and we have the write address. Okay, so we don't know what data that is coming from this mux back to the register file. Let's suppose we have the data as 1000. Okay, so 1000 will be written inside the location 2. That is, 6 will be replaced with the value 1000. Okay, and say we have something like 6, then the first location is 5, which will be replaced with 6. Okay, in that case, if this is the case, then here we are trying to read 1, right? We will be reading the value as 6, not 5. You getting it? Any questions? This is how the timing diagram of register file. Any questions? Okay. So let's go to the yeah.
So would like A1 and A2, 1 and 2, would that be like S and T? Wait, yeah, S and T in a sense? No?
What is SNT?
Like RS, RT.
Yeah, RD1 and RD2 are nothing but RS and RT.
Okay, that makes sense.
Actually, nothing but these values, you can consider them as RS, RT, and RD. Okay. So yeah. So next is ALU block. As we know that ALU has 2 inputs, operand A and operand B, which are of 32-bit length. Okay. This can be either immediate value or the value from our instructions. That depends on the mux output. Okay. So we had the mux over here, and the output is the operand B. Okay, and we have the output as jump branch. As of now, like just ignore these 2 outputs, and you have the output as ALU out, right? It is 32-bit length, and you have the input as function. So based on the function, you will do the corresponding operation. So this function decides what operation the ALU does. So based on that, you will get the output. Clear? And those operations are given in the table. These are the operations. So for this lab, you will be implementing all these instructions. Okay. Yes.
So we don't have to implement the branch part, the function,
Which part?
the branch.
No, not for this assignment.
Just ignore the branching and constructor in the list. There's like a list. You would ignore those.
Yes. You won't be implementing branch. So next block is data memory. So you will be using data memory only for load word and store word instruction. Only for these two. Okay. If it is other than these instructions, you won't be using this data memory. So data memory or it is RAM. So you have in this you have 512, 1, 2, 512, each of 32 bits. Okay, and you have the input as address, which is the output coming out of the ALU. And you have mux, this select line, this is mem to reg. I'll go through the select lines later. So this goes back to your register file, write data. Okay, this goes to write data. This is of 32 bits, and you have write data, 32 bit address, and read data, and this is the address, and you have write enable. Okay, so you will be using data memory only for load instruction and store instructions. Okay, if you are doing some other operation other than that, then even though that the output of ALU goes inside this data memory, this select line will select this select line will select this value if it is either load instruction or store instruction. Okay, if you are doing instructions other than this, then you will be selecting this value that is directly coming out of ALU. Okay, that selection will be done using this mux and this select line. I will explain which is the select line that you are using and the cases later on, because when I explain the controller, I can explain you this part. But that is why you have the data memory, either to write data or write data or read data. If write enable is high, then you will write the data to this into data memory. If write enable signal is low, then you will read the data. So this is the write data. You'll get the 32-bit value from this pin, and you have the address over here. This address will specify where exactly you will be writing or reading the data from the data memory. Okay, so this is the operation of data memory, and the data that is coming out of mux will be written inside the register file. The address will be specified using this RD. Okay. Any questions? Yes.
I guess there's a reason why, but why isn't that you can't just grab it immediately after your ALU calculates your value? Why can't you just use that immediately? Why do you have to wait for it to still store in memory? Like if it was like store word, why can't you still use that line directly from the ALU? Is it just to make sure that there's no errors? Like, why have the mux basically at the very end? Why can't I just grab it every time directly after the ALU calculates?
Like you're asking me that why do you want to take this to the A
Why do
max
we have
instead
that?
of taking it directly?
Yeah, why do we have that component?
It's because when you do the load word, it will be something like $2, okay, 0 of $1. Okay, this is the immediate value. Okay, so the address will be stored in this location. Address, this is like something like RD. Okay, this is immediate value, and say this value corresponds to 1. Okay, this value addressed to some location which has value 1. Okay, so this is nothing but add operation. So you will do immediate sign extended, that will be nothing but all zeros plus $1, which is all zeros and 1. So this add operation should be done using the ALU. This add operation is done using ALU. Okay, so the processor doesn't know whether it has computed a value or an address. That has to be filtered using this mux. Okay, so that has to go inside ALU and you cannot directly write. It has to get filtered, right? You don't know whether the processor doesn't know whether it has calculated an address or a value of 32 bits. So that is why you have to use the mux to select between those two values. Okay. Are you familiar with store word? Should I explain that? Store word. Okay. Load word is something that you access the data from data memory and you store it inside register file, right? But store word is opposite of that. You will access the value from register file and you store it inside data memory. Okay. Say you have another instruction. Let's consider the same instruction. Store word. Okay. So this will be the RS. Okay. Okay, so this is the location where you have to, this is not exactly RD, but this is the location where you want to store the, this is the, okay, so this is the location where you exactly store the data. Okay, no, sorry, this is the something like RS. So this is the address where you get some value. Say that you have value as 6. Okay, this $2 will corresponds to some data inside register file, right? That will be output of the RD2. That is nothing but the write data, which is value is 6 here. Okay, and this is specifies the location where exactly it want to store the data. Okay, so it is 0 plus say $1 is will give you value 1 because this is an address. Say something like RD and it gives you value 1. So you have to do add operation and to add it to 1 and you'll get the value as 1. So this will be the address, right? So that address will be the output of ALU. Okay, output of ALU, and that goes inside the data memory. This is the address. To that address, 6 data will be written inside the data memory. Okay, so that is the operation of store word. So this specifies what exactly the value, and this specifies the address where exactly you want to store the data. Okay, this is store instruction. Okay, so this is the data path. Do you want me to explain one more time? I'll start from the program counter. I think it will be even more clear for you.
Sure.
Okay, so initially your program counter will be reset, so it will be 0. All 32 bits will be 0. Once reset goes slow, it starts incrementing, it starts counting. Let's say the value changes from 0 to 1. That will be, you'll get 1 because of adder that gets incremented from 0 to 1. So that 1 goes inside, the 1 value corresponds to some data. It is an address that corresponds to some data inside instruction memory. So you'll access that 32-bit, which is a 32-bit address for your MIPS. Okay, you'll get that value, you will decode it. When you decode it, you will get the RS, RT, RD, function, upcode, and immediate. Okay, so you will feed the RS, RT, RD inside register file, and you will feed the function and upcode inside the controller. Okay, controller takes care of the controlling. I'll explain that later. And you will feed the immediate inside sign extender. Okay, sign extender will do the sign extension operation, so it will extend from 16-bit to 32-bit. You will feed that 32-bit value inside the MUX. This RS value corresponds to operand A, so that RS will be pointing to some data. You will fetch that data and you will feed that to the ALU. RT corresponds to the second operand. So that will be pointing to some data, so you will fetch that data and you will feed that to the MUX. But your processor doesn't know whether you're doing R type of instruction or I type of instruction. So this MUX has to select between these two values. That selection will be done based on the control signal, which will be fed using the controller. Okay. So say you are doing R type of instruction. So operand A and operand B, both are coming from the register file. That will be fed to the ALU. ALU has the input function of 6-bit, which selects the corresponding operation. So based on the function value, you will do the ALU does the corresponding operation, and it will give you the output. Okay. That output will be fed to the data memory, and it goes to the MUX at the same time. So your processor doesn't know whether you're doing load word or store word or any other instructions like R type. Okay, it doesn't know. So based on the select line coming from your controller, that is fed to the MUX. Okay, the 32-bit address that is fed inside the data memory will give you some data. Okay, depending on the write enable. If write enable is high, it would have returned the data to the corresponding address. If write enable had been 0, then it would have read the value. Whatever it may be, you will get some value at the input of the MUX from the read data. So your MUX job has to select between these two inputs. Based on the instruction, it selects the corresponding inputs, and it gives back to the feeds back to the register file. So your RD, that is the address location where you want to write the data, will be returned in the register file at the positive clock edge, and write enable has to be high. So write enable is synchronous with the clock. Okay. So this is the operation of the MIPS processor. This is the data path. This is the operation. But how to control, that will be taken care by the controller. I'll explain that like after a few minutes. But now you are set. Any more questions? Is everything clear? Okay. If you are comfortable with the data path, then I would suggest you to build each and every block. Don't just try to integrate them. I would suggest you start from the left, build the program counter, run it using test bench. Make sure that your program counter is nothing but a D flip-flop, okay, with a synchronous reset. If your D flip-flop is working fine, then add adder to it. Then make sure it is counting. You're getting the right waveforms. Then build your instruction memory and check it individually, standalone. Okay. Once your instruction memory is working fine, then integrate that to these program counter and adder. Then check the output of instruction memory. Like that, build each and every block individually, test them using your simple VHDL test bench. Okay, you can use VHDL test bench. Test them, make sure that it is working properly, and integrate them. Okay. So build it step by step. It will be easier for you to test it. Okay. And this is about the data path. Okay. And you can you have to build a system Verilog test bench. We will give you the test bench. You have to template. Based on that, you have to customize that to your design. But as of now, for like the rest of the 2-3 days, you can start working on this. Okay. In the meantime, we'll give you the test bench. So this is about the operation of the MIPS processor, basic MIPS processor. So and I'll explain you the controller later. Any questions? Okay, you can start working on this. Again, you can start building the blocks. Okay.